Hello, my name is Mads Wilson, and I am from Copenhagen, Denmark. And I'm here today to tell you about how to build rockets in your garage or wherever you want to. You won't be able to, well, maybe you do. It's not my aim that you will be able to go home today and build a rocket, but I'm going to tell you a lot about what is going on, how it is done, and all the pitfalls, because there's a lot of pitfalls that you will encounter during the way. I am part of a group called Copenhagen Suborbitals, and we are, to my knowledge, the world's only amateur manned space program. So our aim is to build a rocket that can put a human being in space. And we work out of a, let me get this working. We work out of a old shipyard in Copenhagen, or one of the small buildings in the shipyard. That green building. I don't know if you can see the screen here. And incidentally, this picture is taken a day where the ISS, the International Space Station, went over Copenhagen. A very special day, and I'll come back to that later. So, we are not trying to build a rocket that can put a human, send a human to the moon or circumvent the globe or anything. We're just trying to build a rocket that can do the same as the Americans and the Russians did back in the 50s, send a human over the Kármán line. The Kármán line is 100 kilometers up, and that is the official boundary to space. This is not something out of pure fantasy. We have, to this date, launched multiple rockets. The first one was the Heat 1X in 2011. This was a not very good rocket. It was slightly banana-shaped, and it flew longer sideways than upwards, but it was a good first step. Then we have tested some capsules, this one in particular with the launch escape system, and we have flown some rockets with active guidance. This one never flew, it was close. And right now we are building the Speaker 1, which is going to be the class of rockets that eventually will put a human in space, or hopefully. We are launching, or we were launching from the Baltic Sea, as some of you might think. Launching rockets in the Baltics is not a very good idea these days. So we are currently working on a different plan. There will be a press release in a few days, I think, or maybe next week. We have just found another way where we can launch in the North Sea instead, in the Danish part of the North Sea. That's going to be very exciting. But we used to launch here in the Baltic, and the reason for this is that launching from land in Europe is difficult. Here in Portugal, there's a very good spot, and I think last week or the week before, there was a competition, a student competition launched here in Portugal. Portugal is very far down the line when it comes to land launches. So maybe we'll have a big rocket launch from here also someday. But we do it here. In Northern Europe, at least, there's not much free land, or there's not many places where you don't have anyone living. And obviously, when you launch a rocket, when it goes up, it will also come down, so you need a lot of free space so that you can have a safe area. Back in 2010, when we started all this, we were searching for a suitable area, and we found this area here called ESD 139, which is a NATO military shooting range. It was designated somewhere after the Second World War, I think primarily to piss off the Russians, because this is close enough that you can do missile tests, but it's not close enough that they can fall into or they could fall into the airspace of the Soviet Union back then. ESD 139. The good thing about this place is that it is designated as a launch site. It is in international waters, but it is still within the European Union's export zone, meaning when we bring a rocket there, we don't export rocket technology outside the European Union. I will also come back to that later because that's an important point. And it has an unlimited ceiling, meaning that we can just call air traffic control in Malmö and say at next Wednesday, 1600 hours, there will be a launch from ESD-139 to unlimited height, and they say, yes, we will redirect plane traffic. In theory, at least. Of course, it is not that simple in practice, but in theory, everyone is allowed to go there and launch rockets if they want to. As I said before, probably not a good idea these days. But sea launch has its difficulties, because you cannot just take a truck, drive a rocket, put it on a ramp, work on it, and launch it. You need to sail it out there. And anything that has to do with ships is complicated. Weather is all of a sudden a very big deal. You need not too much waves. You need all kinds of support ships. This is our main vessel, an old North Sea fishing boat that we have rebuilt for the purpose. And you can see a lot of small boats intended to take people back and forth from the launch platform. So everything needs to be planned really, really well, because if you stand on the platform and realize that you have lost a screwdriver or forgot it, then you cannot just go to the toolbox and take it and go back. You need to radio for a boat that will come and pick you up, go to the main ship, and then hope that someone on the main ship remembered the screwdriver. We also had to construct a launch platform. You can, of course, buy commercial platforms like the one SpaceX are using, but they're expensive. So we built one ourselves. And we are lucky enough that every time we do this, it creates a lot of attention. So we, for example, you can see in this picture, the Danish television Channel 2 news helicopter were kind enough to be there all day and cover the event. And we also have airplanes from private plane clubs that support us by covering the airspace and taking photos from above and all that. There's a lot of computers, there's a lot of electronics involved, and everything needs to be set up on the boat every time. So you can, as you can imagine, it's quite a big hassle to do this. When I said before we're trying to launch a human in space, some of you might think that sounds difficult and dangerous, but we are working from a principle of just good enough. Meaning that we are not trying to push anything to the limit. We are not trying to maximize efficiency. We are not trying to get the most out we can of something. We are just trying to build something that is just good enough to fulfill the purpose. And the main purpose here is not killing the astronaut. So sending him to 100 kilometers, bringing him back without, or her, without killing the passenger, right? That's the main thing. And just to give you an idea about scale, if any one of you are following SpaceX right now, this is Starship. This is the Falcon 9. This is the Blue Origin's, Jeff Bezos' little funny thingy. And this is our Speaker rocket. So you can see we are not in any way in the big league yet. But just building this is difficult enough. I have brought a little demonstration, a little 3D video, so you can see how the event will go and how the flight will take place. Can you put some sound on it, please? No sound? No. Imagine sitting there on the top of that rocket on a floating platform at sea, just slightly waving back and forth, waiting for that engine to be lit. If you don't get seasick from the way up, then you will surely when you're waiting on the platform. So the whole idea is that the engine will burn for about 90 seconds, sending the rocket approximately 50 kilometers up, and then there will be enough inertia in the rocket so that when the main engine cuts off, then it will coast another 50 kilometers, and then the capsule will separate from the booster. The booster will come down in the parachute, and the capsule will also come down in a parachute. And remember, this is only 20 kilometers more than what Felix Baumgartner did back when he did the parachute jump. So you can see the capsule separating from the booster. And then that little thingy you saw coming out is something called a balloon, and that's because when we are going down, all that energy that has been built up in the rocket coming up, that needs to be put somewhere, and the only way it can really go is by heat in the heat shield of the capsule. So we want to make sure that the heat shield is pointing downwards the right way. And the way you can do that is by deploying a little parachute kind of thing. It's called a balloon. Its only purpose is to create a bit of drag so that the capsule will face the heat shield downwards when it's coming down. And this is the most dangerous part of the whole flight, going back down from space. It will come down, but the question is if we can keep the astronaut alive on the way down. The parachutes are then reefed, meaning that they are not fully deployed, and then once enough speed has been taken away from the capsule, then they will open fully, and the capsule will splash down and land safely in the water. Hopefully not too far away from the launch site, so that we can go and pick him up. This is how the mission looks. As you can see, it's quite simple, really. The most difficult part is from what happens up here and until he or she, the capsule, hits the water. And that is because on the way up, we can control the rocket. I'll get a lot back to that later, a lot more, what I mean about control. But we can control the rocket when it's going up. Remember I talked about before, good enough, right? And not killing the astronaut. If you think about, you have all seen the Apollo missions, right? And you have seen the Apollo capsule. After all those missions, that shape came to be known as an Apolloid, the capsule. And there's a reason why that capsule is shaped that way. Mainly because, and also the size of it, that is mainly because that is what fits an astronaut when he's lying on his back. And it turns out that orientation of the human body is the best when you are being propelled with heavy g-forces that way. And I'll also come back to that later. That was something that was figured out back in the 40s and 50s, where the American Army, they did a lot of experiments on humans, human volunteers, to see how much g-forces the human body could withstand. And what they did was they strapped people on a rocket sleigh in the desert like this and accelerated them to about 800 to 1,000 kilometers per hour. And then they were braked just within a few seconds to a full stop. And then after that, examined by doctors to see how that affected their bodies. It doesn't look very pleasant, but they learned a lot from it. What they found out was more or less this. This position, standing like this in a rocket, that would be not the total worst, but almost the worst. Because when you stand like this and you're being accelerated that way, then all the blood will disappear from your head, and you will faint. And if the acceleration continues, then you will die within 30 seconds to a minute out of blood loss. It would be worse if you were standing on your head, but I guess that is not really in the picture. That would be impractical. Because then the opposite would happen. All the blood would be in your head, and then all your blood vessels would burst, and you would die from too much blood in the head. Backwards, this way is not so bad, but the best is the other way. The only thing is that your eyeballs can be a little unhappy, that they can either distort or pop out, and it's supposed to be very unpleasant, but it's not very bad. You can survive it. So going that way, and that is why the Apollo capsule is shaped that way, and why the astronauts are lying on their back, because the best position is being curled up like this on your back, so that you have your extremities close to your body and all the blood in the torso near the heart. The next best thing is what the Russians designed in the Soyuz vehicle, the Soyuz capsule. It's called the cashback position, where you sit still like this and you're tilted slightly backwards. So you're not entirely on your back, but tilted slightly backwards. That also means that the forces, the G-forces, when you're accelerated, they are not directly up your spine, but they are sort of perpendicular to your spine, like this a little bit. Not fully, but a little bit. So your spine won't crush. That is also a thing when you are accelerated that way, that your spine can crush completely. Not a good thing. And then we're not talking about pogo effects, if any of you know what that is. Pogo effect is oscillations in the rocket where it acts like a pogo stick, meaning that your spine would be stretched and pulled together and stretched and pulled together, and then you would die. So this is our capsule design. You can see the astronaut being in there. He will just be able to fit in there, and he will be in the cashback position, slightly tilted backwards. We have a couple of doctors on our team, and they have assured us, they're not going to assure me because I'm not going in there, but they assure that the person going in there will not die, at least not from the G-forces. Might faint, but will not die. One other thing, and one other reason why the capsule is built this way, is because, again, the good enough approach. Instead of, remember, we don't have much money. We are funded by people like you, really, people who follow the project and give us a little money every month because they think what we're doing is fantastic. We don't have the money to send out the design papers to a factory and have them build a capsule of some size. We need to do it ourselves. And we found out that a capsule 1 meter in diameter approximately will be perfect for an astronaut in that position. And if you buy steel or aluminum plates in standard industry size and you roll them, then you get a tube of 98 or something centimeters. That's good enough. And that saves us a lot of money because then we can just buy standard plates that you would use for shipbuilding or whatever, and round them, and then we have a tube, and then we can weld up a capsule. And it doesn't need to be round. Difference in shape that way is not a big problem. The other direction is a little bit worse. We don't need a rocket, as I said before, that is banana shaped. We need something that is sort of straight, but it's not that much of a problem. Back in 2014, we thought we knew everything. We started out in 2011 by building a hybrid rocket. That was the one that I talked about before, that flew more sideways than up. And for a lot of reasons, if any of you are really into rocketry and you don't know beforehand, go home and go on YouTube and look at hybrid rockets and delve into that rabbit hole of all the weird things that happen in a hybrid rocket. But we had built a couple of big liquid rocket engines, and we thought, well, what can go wrong? Let's just build a big rocket. And instead of testing it, or instead of testing the components, shouldn't we just build the rocket and put the rocket in and strap it on a test stand and do an all-up test? Because it's like how you build software, right? Just build everything and test it, and just, at least that's how the Danish government builds software. Build everything and test it and hope it works out. We did that, and this is what happened. And I'm very sorry that we don't have any sound, because this is amazing. What you see now is the pre-stage here. When you ignite a rocket engine, you have a pre-stage and a main stage. And pre-stage, that is because you need to get the combustion going before you ramp up and push all the fuel and oxidizer into the engine. And in a minute, you'll be able to see right up here, there is, you saw it there, just when we moved into main stage, just when we opened the valves, there was a crack, a small crack, about 10 centimeters in the wall of the rocket engine. And That small crack meant that all 600 liters of fuel came out in about 5 seconds. And at the same time, all the liquid oxygen was just pouring slowly into the fire, so everything burned. The fins on the rocket burned. And that video here, the only reason why we have it is because there was a small GoPro camera that was put with cable ties about 2 meters from the rocket. And it got so hot that the cable ties melted just before the camera melted. And then it tilted and spun and fell down into the water pit below. And our electronic guys, they managed afterwards to take it apart and pull out the memory chip and get that video. And the camera is of course completely dead. But after that experience, and a fantastic thing about being with people who are passionate and do this. Remember, we are not paid; we just do this for fun. I remember I was standing in the control booth that day, a couple of 100 meters away, and once the smell of alcohol had disappeared from the test area, we use alcohol as fuel. I was looking around, and people were like, ugh. You could just see their eyes. They were thinking, "Fuck, we have spent 2 years building this thing, and now it's just gone." But then, 5-10 minutes later, people were starting to like, okay, let's go build another one. And that's what we did. Or, well, we went back and we thought really hard about what we had done, and then we figured, okay, we need to take a different approach. We need to be more systematic. We need to design and test components individually, and we need to find out what is it that we are building. What are we aiming for? Not just building a rocket or building a rocket engine, but being a little bit more systematic. And that came to these 2 rockets, the Nexø 1 and the Nexø 2. As you can see, they are similar. The Nexø 1 is a bit shorter, and that is because this is a simple version using something called pressure blowdown. I'll talk about that later. And this Nexø 2 up here is almost the same technology as we will be using in the Speaker rocket, with something called dynamic pressure regulation that has to do about how the fuel is being pushed down into the engine. And the whole idea with these is the only thing you cannot scale when you're building rockets is the engine. Everything else, the radio systems, the telemetry, the computer systems, the guidance, everything can be scaled because it is exactly the same. So what we wanted to do with these 2 rockets was we wanted to test the flight profile. See, can we build a system of electronics, computer, hardware, programming, all that stuff that can give us the flight profile and see that done with 1 or 2 rockets, and then we transfer that into a bigger rocket afterwards. Does it make sense? So we ordered a lot of parts. We had a little bit more money back then. We ordered. You can see it's like an IKEA set of rocketry. We ordered parts for 2 rockets, and we designed a rocket engine for this called PPM5. Also, you can go to our YouTube channel or website and read a lot about. I could talk about this one just for an hour. You can go and look that up and see all the details. That was a fantastic journey, just designing that little rocket engine. And then we were about to launch it. Before we go there, before I'll show you all the launch data, I will talk about the most difficult, and this sounds so stupid if you don't know anything about physics or mathematics. The most difficult part in launching a rocket is to determine which way is up. And I'm not kidding you. It seems simple, right? You put the rocket on the platform with the pointy end up, and then you launch it, and then you know what is up and what is down. And that is also correct in theory. But once the rocket leaves the platform, you need to control it. You need to guide it. Remember we talked about before the astronaut sitting up there, and we don't want him to be crushed by the G-forces. The easiest way to guide a rocket is the same way you do with what we see now on television, these Earth-to-air or Earth-to-Earth missiles that comes out of rocket launches. That's the easiest way. The easiest way is you just give it a shitload of acceleration. We are talking maybe 20, 30, 40, 50 Gs. And then you spin it a little bit, just like a rifle bullet. Have any of you studied physics? A little bit? Okay. So you know, when I do this, you know what I mean? Spinning, when you spin something, then you will get a resulting force that way or that way, depending on the direction. And that's why you spin a rifle bullet, for example, or you can spin a rocket accelerating. That will create a very stable motion in the direction that you are pointing. But if you want to put a human inside, that is a very bad idea. A lot of acceleration plus a lot of rotation, a very bad idea. You want something that moves slowly so that you can control the motion and you can control the g-forces so that you're not killing the astronauts. And this is a very, very simplified drawing of that, of what you need to control. You need to have a flight direction, and you always see rockets with fins. The fins on a rocket, they only work for the first 8 or 10 kilometers. What you use them for, you use them to create drag in the atmosphere, just like shooting an arrow from a bow. The same principle. You use them to create drag so that you have a center of, it's called a center of pressure that is as far back as you can, and then you have the center of gravity or center of mass in the rocket, and that is, you know, if you take a ruler on your finger and balance it, if the ruler is completely made of the same material, then the center of mass will be in the center. If you drive a nail through the one end, then center of mass will most likely be towards the nail somewhere. That's the center of mass. And that is important in a rocket. You want the center of pressure, when you have air drag, to be as far backwards as possible, and you want the center of gravity or center of mass to be as far ahead as possible. The Chinese, when they invented the rockets that later were used by the British to destroy Copenhagen in 17-something, they learned this, and they solved it just by adding a stick to a rocket. And this system is quite simple because the center of mass doesn't change much because what weighs the most in these kinds of rockets is the canister. It's made of paper and clay and a little bit of gunpowder, and then you have a long stick. So it'll create sort of a fine ballistic flight, and the stick is only used to create drag in the air. A normal dart, exactly the same principle. You have a very, very light tail end, a very heavy tip, and then some fins to create drag, and then your dart will fly straight. It is not quite that simple with a rocket. You have the fins, and the fins will help you a little bit until the air gets too thin at about 8 or 10 kilometers. But other than that, you need a way to control the flight. You need a way to control the flight direction. This is the very simple coordinate system. You need to control these 6 axes of freedom. Roll in both directions, roll that way and roll that way. Pitch, yaw, and roll. Same as on an airplane. And the way you can do that is by either gimbaling the engine. You have seen that on SpaceX videos, for example, where you can see the engine moving down there. You're just putting thrust at a slightly different angle, and that will then move the tip of the rocket relative to the center of mass. Or you can do as they did on the old Atlas missiles, add small rocket engines on the side, same principle. Or you can do as we did on the Nexø rockets, and the Germans did back with the V2 rockets, put a little jet vane in the exhaust stream of the engine. That pushes some of the exhaust to one side, and that will then direct the rocket. If any of you have worked with engineering problems at any point, it is the balancing stick problem, really. Have you seen these little robots where you put a stick and then the robot's purpose is to not have the stick tip over? It's the same in theory, only that it's slightly more complex. Because you don't need only to make sure that one end is up and one end is down, you also need to control roll, pitch, and yaw. And to make things worse, you also down here have a thrust that varies. And as the rocket gets depleted from fuel, your center of mass will also change. So the center of mass is not at the same spot. It will move downwards, and that changes the algorithm that calculates how the guidance system should act to the movements of the rocket. Again, this is actually also a simplified coordinate system. And even with all this, we still haven't solved our main problem that I talked about before, which way is up. Because this is done with accelerometers and gimbals, for example. But they also need to know the initial starting point. What is our alignment vector? What is the way up? There's a lot of hacks how you can do it, but I'll give you a small hint here. What you see in the background is the gyroscopes of the Saturn V rockets. And this down here is a little 10 degrees of freedom module with a magnetometer, accelerometer, and a air pressure sensor that you can buy on eBay for 20 bucks. And this little module does more than this do. This is the technology we're using now, and this is the reason why we can do this. Had we rewinded time 50 years, when this technology was the only thing available, we wouldn't be able to do it. That being said, this module is not good enough. The reason why these modules, if any of you have played with those, they are difficult enough to make work as they are, but the reason why they work is because they do a lot of cheating. For example, if you have your cell phone, have you ever thought about that when you play a game or something, even though that is it is a quite cheap accelerometer that is in your cell phone, but somehow it almost always knows which way is up, and you don't really calibrate it other than doing that weird 8-figure movement when you start up the phone. That's because they're cheating. When you're close to the ground and when you're not moving fast, then you always have the 1g force vector going down towards the center of the Earth, and they use that as a reference, so that they use the magnetometer to have an upwards arrow, or it's actually a downwards arrow all the time. You can do that in a rocket, but in a big metal object flying 3 times the speed of sound, accelerating with 5, 6, 7 Gs, it's not trivial. GPS is also a possibility, and it can be done, but the American military found ways around that when they released the GPS system to the public back in the 80s or something. The military GPS system is precise enough to do that, so that you can have one at one end and one at the other end in the rocket, and that coordinate system can be aligned. But the commercial version is not nearly precise enough to do that, but it can be done. And that is, for example, how NASA and SpaceX are controlling a lot of their things by using these interconnected GPS systems. That being said, we are not using that Arduino module. We're using something that costs, I think, a factor 100 more or something, but it's still cheap. And we are measuring accuracy not in seconds, but in minutes. So we have some, you can buy from Analog Devices some modules that can maintain correct direction about 3 to 4 minutes before they just go haywire and don't know which way they're pointing. And they cost about $3,000, $4,000, $5,000 or something. But it is still extremely cheap compared to this one that were made from moving wheels. I will show you now, and again, I'm very sorry that we don't have sound because this is fantastic. Actually, you know what? I think I'll just pop this out and hope that you can hear something from my laptop because the sound of this is amazing. Oh, you can't. This is the flight of the Nexø 2. Sorry, the Nexø 1. Let's try. Maybe it works. Yeah, it does.
We are losing power.
Kommer ned nu. Jeg kan se. Jeg kommer ned.
This is Fido here. I have no altitude on the
Kommer
rocket.
herned. Jeg
Kommer ned, ja, vi kommer ind i også.
Der er ingen go.
Der er ikke.
We have a rocket in free fall. The parachute is going down. And we have splashdown.
It sounded like that.
Yep.
Exactly like that.
Yep.
What you saw here on the video was a rocket, the Nexus 1 rocket that ran out of fuel. And it ran out of fuel, or it came down the way it did due to bad testing of software. Remember I talked about all these parameters that you need to be able to control. One of them is engine pressure. How much force the engine is producing so that the guidance system knows what to do. It was a very warm day on the Baltic Sea, and we didn't really at that time yet have devised a good enough system to measure how much liquid oxygen we had in the tanks. Liquid oxygen is minus 183 degrees or something. It's not something that you just pour in a can and then pour over in a tank and then you know, okay, now I have 20 liters because it's boiling at room temperature. So we try to weigh it and all sorts of stuff, but it doesn't really matter. The point is that there was too much pressure in the oxygen tank, and since it was the pressure in the tanks that fed the engine, then a difference in pressure that resulted in a wrong mixture of oxidizer and fuel in the engine, and that again resulted in a wrong engine combustion pressure, and then you have a bad cycle because then the pressure against the tanks got weird, and then the pressure in the tanks got even weirder, and then it just spent too much fuel, so it spent all the fuel too fast. And then at about a kilometer, 1.2 kilometers or something, the engine just cut out because there was no more fuel. But the computer that were monitoring it said, well, that can't be because I'm only 1.2 kilometers up. That must be a pressure sensor malfunction. I'll just continue. And how would you know? How would you know if it's a faulty sensor or an engine that has cut off? It is a good example of even if you test and take into account a zillion different scenarios, it is almost impossible unless you have redundancy upon redundancy upon redundancy. If any of you are into that sort of thing, there's another rabbit hole. Go and look at how the NASA designed the space shuttle computers and how they were interconnected. Well, you had basically 4 or 5 computers negotiating all the time about what was the correct solution. You can go on forever with that. But the rocket simply ran out of fuel, and the computer didn't react as it should. That was problem number 1. Problem number 2 was the state machine inside the guidance system. Because our flight director, Thomas, who was controlling the rocket that day, he saw it and he said, okay, this is a problem, it's coming down, we need a parachute. So he pushed the parachute button. But the guy who wrote that part of the software didn't expect that order of sequence, so he didn't think about, in the state machine, that if you press parachute, and the event before that, which is nose cone off, if that didn't happen, then you shouldn't release a parachute. You should go back one step and push the nose cone off and then release the parachute. So on the data from the accelerometer, you can see like a and that was the gas generators in the parachute compartment going off, but that was not enough force to push out the nose cone. So you can just see an explosion within the rocket, and then it turned and came down and crashed into the ocean, still boiling off liquid oxygen. And the interesting part, at least what I think, is the data from the accelerometer, because we got all that. Here you can see this is a simulation that is created from the data that we got from the rocket, where you can see exactly how everything went down. Look at the velocity here. You can see for the first 50 seconds, everything is fine. It is only off by a little bit, and then it starts to move slightly to one side. And these numbers down here, they are a result of that instability problem. And now the upward speed is declining, and then you see the minus. It means that it's beginning to come down.
Det kommer ned.
This is Fido here. I have no altitude on the
Den
rocket.
kommer herned. Ikke?
And the only reason why it stabilizes is because of the fins, because it's a little bit heavier down here than up here, and then the fins will create drag, so it'll come down. And then it hit the water, and you heard that before. You can see that it got pretty beaten up, but we managed to recover it. The damage down here, and this is from the impact. The damage down here is because we estimate that it had been somewhere between 40 and 50 meters below surface. So this here is simply crushing by water pressure. The inside of this compartment was filled with the styrofoam, so there are air bubbles, and that was just being compressed by the water. You see, that's pretty beaten up. Everything but the nose cone. That is somewhere on the floor of the Baltic Sea. Fun fact: the Nord Stream 2 pipeline is right under the launch area, and we have lost quite a few over the years parts in that area. So back earlier this year, was it last year, when they announced that they had found strange military-like objects close to Nord Stream, we were all like, oh fuck. Because we have quite a few strange rocket parts on the bottom of the Baltic down there. Yeah, the Nexus 2 is not very interesting, really, because it all went perfectly and the rocket came down in a parachute. Again, if you want to dive into this, go to our YouTube channel and watch the videos. It's fantastic. It was a fantastic day. But from an engineering point of view, it was, yeah, not so interesting. And then there's all the other stuff. People are always like, oh, you build rockets. They focus on the rockets, right? And everyone, usually when people want to join the project, it's because they want to build rocket engines. And sometimes people get discouraged when we tell them that it's only about 20% really that is about the rockets. 80% is all the other stuff that is around it, because it is a huge operation. This is kind of how we are organized. We have a very flat structure, but this is, at least in theory, how we are organized. We have a booster capsule, marine, public relation, electronics, and then we have the support group, which hopefully are you guys. And then we have a board where we have a board that is elected every year, so it shifts from year to year. We don't have anyone in particular running the organization. It is elected by the members every year. We have at least 1 or 2 times a year we have seminars where we talk about plans and how to interface with each other. You can see that this was held in a kindergarten, because our chairman at this point was a kindergarten teacher, which is somewhat telling of the organization sometimes. Can you imagine 50 socially incompetent nerds being at the same project, trying to interface and agree? And no, it's not always a good idea, but it's fun. We have the booster group. They are designing tanks and engines and doing engine simulations and all. I know how this stuff works, like in broad terms and in theory, but they are really into going deep into these design things with engines. This is Joop. He is from the Netherlands. He was an intern at this point, and he designed and built a complete hydraulic gimbal system for his master thesis, and it worked. That was pretty cool. You can see this is the BPM 5 that we did a lot of testing with. A lot of the stuff that we're doing also has to do about building tools to build the tools to build the tool to build the machine. in this case here, for example, this is a tool so that we can do long weldings on the inside of a tank. So we need a tool that can be disassembled and then used to clamp down 2 plates and then do the welding of the inside and then taking apart again afterwards. That took quite some time. It's kind of a simplified welding robot where you have a stepper motor that drives the welding torch, stuff like that. Then we have the capsule department. They are working a lot with aerodynamics. They are working a lot with parachutes. We have this strange rule in Denmark that you cannot test an experimental parachute by dropping something out of a plane. You can only test an experimental parachute by having someone jumping with it. That also is strange, right? So we have a guy called Ahmed. He's a very good parachute instructor, and he does all that. Of course, he has his own parachute. But every time or the parachute guys, they devise something new, then he fearlessly jumps out of a plane and tests our strange, in this case, the balloon. And you can see he has also tested the main parachutes a couple of times. They do a lot of work with that. We have this is experiments with the astronaut seating that we did. They tried to build a mock-up of an aluminum seat and maintaining strength in the seat by at the same time having it as low weight as possible. And then to be honest, this picture is mostly fun because they were fooling around with the orientation, and then they were putting Anna into this autoclave with a Russian space helmet. But the seating is what it is. The rest was just goofing around. We have our public relations. The only way we can get money is by awareness. And the best way to get awareness is to feed all the people out there in the world that like what we're doing and that support us with updates. So we try, and it is a huge amount of work to do it, but we try the best we can to push out these videos with updates and technical details about what we're doing. And there's also a little bit of you need finesse to do this. We have had several unnamed intelligence agencies talking to us a couple of times, because publishing detailed information on how to build rockets out of common materials is not, they don't like it the same. Not all of them think it's a good idea, let me put it that way. So we are very particular in terms of what we can show and what we cannot show. So we will never, for example, show anything where you can devise measurements. We will never give away drawings. We will never give away code. We would like this whole project started with the idea of being open source and having everyone in the world to be able to help us and build on it. It just turned out that in terms of legislation, that is a very bad idea. Because in most parts of the world, at least in the Western world, if you do that and someone misuses it, that is almost a one-way ticket to Guantanamo, no questions asked. In most parts of the Western world, especially in America. Not as bad in Europe, but almost. So we need to be very careful about that. Every time we do a launch, we do a live stream. And today it's easy, right? You can just buy Starlink and then you can live stream from anywhere in the world. When we started this, we had to find a way how to do it on the cheap. So you can see that little white dome up there. If I can point to it, maybe there's no more battery. That little white thingy there, that is an old modified radar dome where we took some off-the-shelf Ubiquiti network equipment and hacked it a little bit. And then this tower, which is incidentally an old listening post from the Danish defense that is now used for something else, we got permission to put up our receiver. And those two are able to see each other at 30 kilometers distance, and we could create a link of about 5 megabits stable, and that was enough to do live video streaming from the Baltic. The first time we used it, we had a little problem because Scott, who wrote the software to control these two, he was very tired when he did it. He did it on the way over there on boat once in the middle of the night where he hadn't slept for 2 days. And then we had, on the day, we had to deploy a guy up there to align the antenna manually because the software he wrote, it thought that the island was spinning, and we didn't have time to correct it. So we had to have a guy up there sitting and stopping the rotor every time it tried to correct for the spinning of the island. That's why you don't write code when you're tired, right? How back then, again, when we started, there was no such a thing as distributed video mixing, really. So Peter, the guy in this picture, he wrote from scratch a distributed video software video mixer that can control cameras on a remote unstable network, taking in packet loss and everything into account. That is open source. It is on GitHub, and it's called Snowmix. If anyone wants to dive into that, it is amazing job, and that's what we use for live streaming. Maybe we'll use Starlink next time because it's easier. And then we have our electronics guys, as I showed before. Every piece of electronic we do is either something that is built by standard boards. You can see that's the HAC RF1 radio board. We have a lot of software that we have done ourselves. This, for example, here is to control the area and assemble GPS data and RPIS and what are they called? AIS data from the ship so that we can see where everything is. A lot of sensors that we use, you can't buy them, so we had to build them ourselves. For example, how to measure how much oxygen is in a tank at a certain point. We have some guys that are very, very good at RF, and they have built all our antennas and receivers and everything to communicate. So it is a huge operation involving a lot more than just the rocket. Especially our marine department, who that platform there, they sail for 24 hours on that from Copenhagen to Bornholm in open waters. And I don't know if you can see it, but the floor, you can see there's some like plywood plates. That's because the whole floor is covered with holes, and they needed something to sleep on with, so they didn't get wet. So they're lying there on a mattress and a sleeping bag while they're sailing 24 hours to Bornholm with 5 knots. And then there's boring stuff like scraping weird stuff off the bottom of boats, and it all takes time and costs money. And that time goes away from building rockets, but it's still fun. So yeah, this is the timeline. You can see Nexus 2 was in 2018, and we are tirelessly. We were set back a couple of years by the COVID, but we are tirelessly building the speaker. And I can announce now that we have a launch, not of the speaker, but we have a launch in next summer from the North Sea. From the North Sea, it will be a Nexus class rocket that we will test on a new platform with a German company called GOSA. And that then will hopefully be our launch platform for the speaker rocket. It has taken a couple of years, but it just fell into place this week, actually. So we are very excited about that. And remember, on my first slide, I showed you that little stripe with the International Space Station. On that day, Andreas Mogensen, the Danish astronaut, was up there. And that was just a couple of weeks before we were going to launch the first Nexus mission. And then all of a sudden, out of the blue, nobody knew, he sent this picture down to us. Like, hey, I'm cheering for you guys. So he brought that little printout with him as one of his personal items on the space station and sent that picture to us. That was, and you get a little bit like, oh. But that was fantastic, that was fun. So, that was it. If you like this project, go to our website and support us. Go to our YouTube channel and spend a couple of days looking through all our videos. There's a lot of stuff where you can see all the details. I hope you enjoyed it. Thank you.